Good evening, all. Let us begin with the practice assignment session of week 11. Before that, 5 to 10 minutes, let's see the revision of lectures from 24 to 36. Previously, we stopped with the review till lecture 23, wherein we were talking about moment generating functions. So, moment generating functions are one way of characterization of a random variable like the property density function. And we also saw that moment generating functions with moment generating functions it we simplify the analysis, and thus we could get to easy problem solving. Let us see one application. If we look at the situation where the gamma diversity is sum of the individual diversities from 1 to m antennas. If we have to find the moment generating function of gamma diversity, then directly we could write them as the product of the individual moment generating functions. So when you have a sum like this and when they are independent, the moment generating functions could be represented as product of the individual moment generating functions. This is one example. Then the characterization of a multipath fading channel started. If R of t is a received signal, R of t is summation over n, alpha n of t e power j phi n of t by t comma tau, u of t minus tau n of t. So here u is a complex baseband signal, and so the impact of the channel h of t comma tau, if we see, it is summation over n, alpha n of t e power j phi n of t comma tau, del of t minus tau n of t. So here h is the h captures the impact of the channel, and we could see that it is actually in two dimensions. So one represents the time variation and the other represents the time dispersion. So h of t comma tau means t represents the time instant at t1, t2, t3, etc. So it's time variation, and at each time, what is the how much is the dispersion that's happening? That's captured in tau, time dispersion. So if we look at it in that aspect, we could say h of t comma tau as something. Imagine something like this. So wherein at the same time t, if we see, we will have multiple taus, tau 1, tau 2, tau 3, etc. And the autocorrelation function expectation of h of t comma tau into h star of t plus del t comma tau is written as rh of del t comma tau. Now this will take the form p naught into Bessel function of zeroth order of first kind. So this is the characterization of the autocorrelation of the channel. Now this Bessel function, the shape of the Bessel function is as follows. So if you're trying to plot the autocorrelation against time spacing delta t, the it looks somewhat like a sinc function, but it starts at a maximum, and then the slope depends upon our Doppler frequency. So if we have a higher Doppler, then we see that it is like it's falling steep. So what do we understand from this is the more steeper your autocorrelation function is, the more faster your channel is like changing. That is, your FD is very high, and this kind of time behavior because of Doppler, if we see it in its Fourier transform counterpart, we could have it's like it will be captured in, as spectral changes between minus to plus FT. So the Fourier transform of this Bessel function is P naught divided by pi fd root of 1 minus rho by fd the whole square, where mod rho is less than fd. So they are Fourier transform counterparts. Now this fading uh, was understood to be a multiplicative factor, and hence if we see the frequency spectrum, we'll have a smearing because of this FD, and this was called as spectral broadening. The more your FD is, the more smeared your spectrum becomes. So this has a direct implication of the coherence time. So if larger is our Doppler frequency, the lesser is our coherence time. So if the Doppler frequency is larger, the channel is varying very fast. So the time for which the channel remains coherent is getting smaller. So TC is given as 9 by 16 pi into FD. And then lecture 25 talked about the GSM system design, how the time slots are, and all those details. Then came to important parameters in characterizing the time behavior of the channel. One is level crossing rate and the other is average duration of fade. So, given a threshold, how much the fading envelope crosses that is calculated by level crossing rate. So NV is given as root over 2 pi FD rho e power minus rho square, where this rho is the ratio of V threshold by VRMS. Actually, it's the amplitude. However, if power is given, then you have to take square root. So square root of PTH divided by square root of mean power. And average duration of fade. So with average duration of fade, we can get an idea of how many symbols that will be affected when a channel is going on a fade. So the average duration of tau bar fade is given as e power rho square minus 1 divided by root of 2 pi fd into rho. Then then came the statistical characterization concepts, the WSS-US model, the wide sense stationary uncorrelated scattering model. Wide sense stationary here corresponds to the time variation component, and uncorrelated scattering corresponds to the time dispersion component. So if we see expectation of h of t comma tau 1 into h star of t plus del t comma tau 2, where tau 1 and tau 2 are the delays because of different multipath components. So this is given as RH of del t comma tau 1 into del of tau 1 minus tau 2. So this corresponds to the WSS component and this corresponds to the uncorrelated scattering component. Basically what we have to understand from this does not depend upon T1 or T2, but it depends only upon del T. Secondly, tau 1 and tau 2, that is the delays because of the multipath, they are uncorrelated. So it's uncorrelated scattering, wide sense stationary model. And expectation of mod of h of t comma tau the whole square is our power delay profile. So how the power in the channel is varying based on the delay. And we have few other parameters what you guys saw. One was mean delay spread, then tau bar square, and then RMS delay spread. Mean delay spread is 0 to infinity tau into RH of tau d tau divided by 0 to infinity RH of tau into d tau. And then in a similar fashion, tau bar square, and then RMS delay spread was square root of tau bar square minus tau bar the whole square. Now, channel in our case is mostly discrete channel. So the mean delay spread, tau bar square, RMS delay spread, mostly we have to express in terms of summation rather than integral. So if we see the mean delay spread, it will be summation over n, tau n, RH of tau n divided by summation over n, RH of tau n. So these are some of the ideas or whatever you saw in the statistical characterization. Then, so this is again a similar thing. The time variation of the Bessel function, Fourier transform, if we see, it was a power spectrum. It is bounded by plus or minus ft. And the power delay profile, as Fourier transform, was a correlation function. Basically, this gave us how the frequencies are correlated to each other. Basically, this also gives us an idea about the coherence bandwidth. And from there, coherence bandwidth is should be greater or equal to 1 by 5 into RMS delay spread. This was studied, and the notion of narrow or wideband channel frequency response. Generally, if we imagine this red curve to be the channel, if we are interested in the small blue bandwidth B1, then our channel appears to be almost flat. However, if you're interested in this pink region B2, our channel appears to be changing. So, it the what to say the notion of narrowband or wideband channel depends upon what is the bandwidth we are looking at, and from this came different classification of channels based on the symbol time period and the signal bandwidth. Now, if the signal bandwidth is lesser than the coherence bandwidth, so that is if it is a narrowband signal like this blue one, then it's a frequency flat channel. And if the symbol period is lesser than coherence time, then it's a slow fading. The channel is almost flat and it's varying very slowly. If it is a narrowband, if the signal bandwidth is lesser than the coherence bandwidth, but the symbol duration is greater than the coherence time, then it's a frequency flat but a fast fading channel. The other two divisions are if the signal bandwidth is greater than the coherence bandwidth and the symbol duration is lesser than the coherence time, then we have frequency selective slow fading, and the other is frequency selective fast fading. So, if we have a frequency selective channel, then there is ISI that is caused, and we need an equalizer. So, this is the basic idea. So, in time, if we see, we have a flat channel, a selective or a fast fading channel. In frequency, we have a frequency flat channel, a frequency selective channel. So, these are the different divisions. And the last set of uh, revision lectures for today is how do we simulate the Rayleigh channel uh, in a computer simulation. So you guys studied about three different models for them. One is Clark and Gans, the other is Smith, other is Jake's model. So the Clark and Gans model, it is basically a filter design. Uh, so for imaginary part separately and for real part separately. There you had the problem that for every FD you had to design a filter, and it was highly complex also. In Smith model, basically we went to the frequency domain. So if you see the one what I'm highlighting here, XR of n converted HR of n. In frequency domain, you did the operation. So it's I50 of F50 of XR of n into F50 of HR of n. So this was the idea in Smith's method. However, in Smith's method, what happened is the problem was the size of F50. The size of F50 is the ratio of the sampling frequency and the frequency resolution what we wanted. So, for example, you even had a NFFT size to be 2 power 15, which is approximately 169 millisecond worth of channel. So, in this situation, it is highly difficult for us to get smaller duration channels. And then, so overcoming all these difficulties, then came the JX model. So basically, if you give the Doppler frequency, sampling frequency, and n into this relay feeding generator, you got ZR of n plus JZI of n with the following properties as we expected. And the early lecture on diversity. Basically, diversity modifies the fading characteristics, such as to get more close to AWGN1. And we saw about selection diversity, we saw about co-phasing diversity, then optimal combining. Selection diversity, we chose the best, the maximum of gamma 1 to gamma m. And the probability of fade was probability when all of them didn't cross the threshold. So it is 1 minus e power minus gamma threshold divided by gamma the whole power m. Approximately, it was gamma threshold by gamma the whole power m. Now, what was the optimal combining method? For optimal combining, Gk was Zk star divided by sigma n comma k the whole square. So it was coefficient diversity weighted by the noise variance. So this was optimal combining, and then we saw what we saw was gamma in whatever we get in MRC was greater than or equal to gamma whatever we got an equal gain combining greater than or equal to gamma selection diversity. And then about array gain and diversity gain. So if we talk about optimal combining, we have the benefits of both array gain and diversity gain sitting in it. Array gain will be like if we see in terms of BER, which is SNR. Array gain will be just a parallel shift, a constant shift in the BER curve. However, diversity gain will have a change of slope itself. In transient diversity, we will be able to get only diversity gain and not array gain. That you guys must be remembering. And if we see in even in transient diversity, even to get diversity gain, you need to know the channel information. However, in Almaty scheme, without needing the channel information itself, we were able to harness the diversity gain. So those are the next set of lectures. I think this summarizes whatever I wanted to review. So, if you guys have any doubts, can I just start with the problem solving session? Consider a two-user CDMA system with imperfect power control. Let mod of alpha 1 equal to 0.8, mod of alpha 2 equal to 2. EBN naught is 6 dB and Q is 64. What are the degradation factors for the user 1 and user 2? In week 11's lectures, you would have dealt with multi-user CDMA systems and about degradation factors. But here, the idea is as follows. So, if we see uplink multi-user CDMA system, we basically have different users and they be spread with G1 to GK different sequences, and then you have alpha 1, and then it should be delayed, and then it will be sent. So, in a different uplink channel. Now, if we want to retrieve user 1's data, we definitely will have to go for correlation based receivers. So, the received signal is R of t, then it's R of t into G1 conjugate of t into dt. So, whatever y we'll be getting will be alpha 1 b1 into root eb plus eta 1 plus the rest of the other term. Summation k is equal to 2 to k alpha k bk root eb into the integral. Now, this will be a desired signal. However, all these things will be considered as noise in a multi-user system. Here, SINR will be EB into alpha 1 square divided by N naught plus EB by Q into K minus 1 into mod of alpha K square. Caused by user 2 will be DG2. So that will be minus 0.965 dB, and with respect to DG1 it will be minus 0.169 dB. Okay. Now, in a similar situation, what is the SINR for user 1 and user 2 respectively? So, the same parameters, you will have to find the SINR. So, you can write down the expression and calculate SINR. So, the idea will be like, since you found the degradation factors, you could directly find the SINR. So, based on these formulas, if we decrease the power of transmission of user 2, which of the following statements is correct? What will be the answer, guys?
D, madam. D. So if you decrease 2, I think that will help user 1.
Yeah. We are, if this value is large, then your SINR is going to reduce. So, if this is small, like if you're reducing the power of user 2, then we're going to have a good SINR for user 1. But alpha to mod of alpha 2 square will be directly proportional to SINR 2. So, it's going to directly affect the SINR of user 2. Okay. So, we have a multi-cell CDMA system, and I of OC is equal to 0.7 of I of IC, and the length of spreading sequence is 128. I naught by naught is 6, and the voice activity factor is 0.75. K is given. What is the SINR of the system? So here, perfect power control assumption is that mod of alpha is equal to 1 for all users. With So how do you find the SINR of the system given the voice activity factor and the interference? Intracell interference and the neighboring cell interference also. Okay. So intracell interference is like the interference it's caused within the cells, right? So it will be K minus 1 by Q into EB, where Q is the spreading factor and K is the total number of users we have. So it's K minus 1 by Q into EB. Say it's approximately K by Q into EB. However, there will be interference from neighboring cells also. But the assumption is that the interference from the other cells is just alpha times intracell interference, where alpha is approximately between zero point 0.5 to zero point 0.6. Now, if we have to find the total interference in the multi-cell system, I naught is IIC plus IOC, that is interference from other cells. IIC is kept same and IOC is taken as alpha into IIC. So the total interference I naught is 1 plus alpha into IIC, which is 1 plus alpha into K by Q into EB, right? What we are asked to find is the SINR. So SINR is EB by N naught plus I naught. So I naught taken out, EB divided by I naught into 1 plus N naught by I naught. Now we have to do the substitution for I naught and then cancel EB. So you get 1 divided by 1 plus alpha into K by Q into 1 plus N naught by I naught. And then we have some parameter called voice activity factor. So what is voice activity factor? Basically, if uh, some some user has nothing to send, very less information to send, it will be spreaded by a bigger spreading sequence with very low power. That kind of in that kind of scenario, it is going to cause only that kind of users are going to cause only lesser interference to the others, right? So that measure is given by this voice activity factor. So SNR with voice activity factor is given as 1 divided by 1 plus alpha into gamma into K by Q into 1 plus N naught by I naught. So if the voice activity factor is less, that is if not all of them have maximum information to transfer, then we have a better SNR.
Madam,
Yes,
here,
sir.
madam, here
Yeah.
gamma is the voice activity factor.
Yes, yes, this.
Okay.
Yeah.
And my other confusion is
Yes.
always about the alpha.
Okay.
Is this alpha is a proportionality between I and IO,
Yes,
right? But
yes.
it's the same thing with assume perfect power control
No, they are different.
They're different.
They are different. They're different.
So that alpha is different.
Yeah. See.
Okay.
Yeah. This is like this alpha defines the ratio between the interference caused by the neighboring cells and the interference within the cell. That is this alpha, which is this point 7. So after getting to the formula, just substitution of all the values, variables that are given, and then you can get the answer. For CDMA system, the target SINR is 10 dB, and the relation between IOC and IIC is 0.5. Voice activity factor is 0.25, and Q is 128. What is the pole capacity of the system?
Madam, the interpretation of pole capacity means the number of users a base station can support.
It's like if imagining that all the users are just around the base station, very close to the base station, how many users in that situation can support? Basically, we could tell it like the asymptotic capacity. So here, as by definition, pole capacity is the asymptotic capacity in the CDMA system. As k increases, like as the number of users increases, then how it becomes is the users, only those which are closer to the base station can communicate with the base station, because that much the interference is going to keep increasing. So now what does that mean is the users around the pole, something like that. So that's why it's called as pole capacity. Basically it's the maximum achievable capacity in a CDMA system. If you see the formula for pole capacity, if we want to find 1 by SINR, it's 1 plus alpha into gamma into pole, k pole by q plus n naught by EB. EB by n naught, if imagining its higher value, n naught by EB could be neglected. Then we'll just have to rearrange to get k pole. This was the example sir had dealt in class, so we just have to look into the formula, and the answer is 34. For the system described in the previous question, if the total noise rise due to interference is 6.02 dB, what is the practical capacity of the system? So what do we understand by total noise rise? Total noise rise is N naught is a ratio of N naught plus I naught and N naught. This is given as 6.02 dB. So this is 4. So now you can rearrange to get the relation between I naught and N naught. So SINR is EB divided by 4 into N naught. So we need EB, which is 4 into N naught into SINR. Now we have to basically bring it to this relation to do the further solving. What we need is a practical capacitor system. We need to find K. So what is I naught, write the expression for I naught, then substitute all the variables, keep k on one side, and get the value for practical capacity. Statement 1. Soft handoff is not good in a CDMA scenario in terms of capacity. Statement 2. Capacity falls as soft handoff uses multiple codes over multiple sectors. What do you guys and get in the statement?
D, madam. D.
It's C actually. So soft handoff is not good because of the reason that soft handoff uses multiple codes or multiple sectors. So in CDMA, codes are the resource elements. So for each sector, CDMA consumes one code. So there are only fewer resource elements to allocate. And soft handoff is not a good choice in a CDMA scenario in terms of capacity. For an L-tab multipath channel, one can get L plus 1 branch diversity using rake receivers. Under near-perfect self-orthogonality constraints, the impairment due to multipath is negligible. Which of the statements are correct? So you saw about rake receivers.
A, madam.
Okay. Actually, answer is both the statements are correct. So I'll tell you how. If we understand, if we look into the idea of rake receivers, basically, if we consider the first branch, so it is you have the signal and then it's multiplied by g star of t minus LTC, and then you do the this integration process and then you finally multiply it by HL star. So if you see the first branch, it you will get YL equal to HL B root of EB plus B root EB summation L is equal to 0 to L minus 1 HL RGG. Basically, this RGG is the kind of cross correlation terms. Now, so this cross correlation terms will be very small. So this entire thing will almost be considered as noise, and then this will be the desired signal. For the second branch, it y of L minus 1 will be same way. H of L minus 1 it will be root of EB and so on. Now, what is our y is the summation of the signals from all these branches. So its summation over L is equal to 0 to L HL star YL. So if we see the desired signal, we have B root EB summation L is equal to 0 to L HL mod of HL square. So we have L plus 1 branch diversity, and because of the self orthogonality property, this term becomes very small, right? So the impairment, whatever we get, is very much negligible. So the desired signal uh, can be recovered. This is the idea of break receiver. To get an idea. Hello.
Yes, ma'am.
Given NL is equal to eta L plus B into root over EB, summation L is equal to 0 to L minus 1 HL RGG of L minus 1, L minus L into TC. So here expectation of NL is 0. This is first statement. Second statement is expectation of mod of NL square is N naught plus EB by Q into summation L is equal to 0 to L minus 1 into mod of HL square. Whether the statements are true or false. Which of the statement is true, which of the statements are false.
B, both are true.
Yes, okay, but let's see how. So expectation of NL that we know because eta L is 0 means, so expectation of NL will be 0. So second is variance of NL, so expectation of mod of NL square. So expectation of mod of NL square will be expectation of mod of eta L square plus expectation of mod of this term square, and then there will be expectation of eta L into expectation of the other. That is, there will be some cross terms. So all these cross terms will go to 0 because expectation of eta L is 0. And if you consider this term, it will be product. It can be written as product of this term into its conjugate, and we have to apply the self orthogonality property, and then what we could see is uh, finally uh, we, we'll end up with EB by Q summation 0 to L minus 1 mod of HL square, because this mod of RGG into L minus L square, this will be equal to 1 by Q. That is the basically the cross correlation between them, or the self orthogonality property. So the answer is B. Both the statements are true.